Welcome, everybody. My name is Ferran Teneri. I'm from the University of Nottingham, and I'm going to deliver this talk, which I entitled Adaptive Covariance Pattern Search. In this video lecture, we are going to talk about optimization, and in particular about a class of algorithms which are called Generalized Pattern Search. Let us see how they work. So, at first, this concept was introduced in 1997 by Virginia Thornton. And what was she saying is that GPS, Generalized Pattern Search, is a deterministic search algorithms, which is characterized by an archive of potential moves, which are called pattern matrix. So these moves are, let's say, encoded inside a matrix, which is called pattern. It's indicated here with the letter pk. As you can see, this matrix pk is the product of a matrix B by a certain matrix ck. Let us focus our attention on the matrix B. What is the matrix B? The matrix B is a square non-singular matrix and is the basis matrix. In a nutshell, it's a matrix whose columns identify some directions within an n-dimensional space. So if we want to optimize a function in n dimensions, we are now identifying n dimensions along which we are going to move. Then we have this trial vector sk, and that is the move of the algorithm, and is a column of pk multiplied by delta k. So this sk is a column of this matrix pk by a certain radius. But as we said, let us focus our attention on the matrix B. So we can imagine here we have got the moves and B are the directions. Let us see now what that means. So the column of the basis B are linearly independent vectors that span the domain where we search the solution. So, for example, if we look into a b-dimensional space, which is a subsection of R2, we have got two directions, B1 and B2, which are the columns of B. And all I'm saying is this pattern search algorithm, this generalized pattern search algorithm, is an algorithm that moves along the directions identified by B1 and B2. And these vectors are the building blocks of the generalized pattern search. Now, the question is, how do we choose the vectors of the matrix B? Because this generalization or this, let's say, mathematical abstraction then needs to be translated into an algorithm that functions and that yields results. So what do we do in order to choose B? I will report one classical example, which comes from the 40s. So a way before the concept of generalized pattern search was introduced. So de facto, this algorithm was already going on, was already used in the 40s by this two prominent scientists of the time, Enrico Fermi and Nick Metropolis. They were not having a computer at the time. They were having some kind of mechanical computational device, which was called Fermiac. And all they were doing was simply to use the directions of the variables, which means in our b-dimensional examples to move along the axis, or if you prefer, moving horizontally and vertically. When we look at the mathematical formulation of this concept, what we get is a matrix B whose column is a versor, where a versor is one vector that has got 1, 1, and all the others are zeros. So, and what we get instead of the matrix B is a matrix which is called identity matrix. So you might think that to have like 1, 0, it means that we move only along this axis. There is only this component along this axis, and the 0, 1, we can move only vertically. So But this solution is definitely the most simplistic, but is it actually the best? Now, I have to take, let's say, a step forward, and it is just to a couple of years ago. And I have to introduce something that my colleague and I have designed, which we called Covariance Pattern Search. So let us give at first a general idea. So we say that we want to use a matrix B as a matrix B, a matrix whose columns are the eigenvectors of the covariance matrix associated with some samples whose objective function is below, in case of minimization, a threshold THR. This looks a little bit maybe confusing, but this is what we were doing. Now let us see more in details why and what this means. So when we run the algorithm, we actually run a pre-algorithm, which we call problem analysis. And what do we do during this phase? We sample points within our domain, and out of this point, we can make an analysis of the problem, and we can find out some special direction for the pattern search. And only when we have these directions, then we may start the search algorithm. This problem analysis is fitness landscape analysis, which is a term which you might find in the literature. So let us look at these examples. Here we have like problems in 2 dimensions, which means that then you may think that your function is a surface in the space. So in this case, we have got a sphere. And what happens is that we sample some points, then we fix a certain threshold, and we retain in a data set only the points that are below that threshold. So that's what we do. So imagine that we have got a sphere. We have found this threshold, and we sample the points that are below. And so in a way, we see this circle that is a projection, and that's related to the geometry of the problem. Similarly, we may look into this other case. We have got what is called ellipsoid function. And if we do the same job that I described, what we have is an ellipse here. This is called Ben-Sigal, which has got a different type of feature. And so the landscape looks like a strike. And you can see here this line, this diagonal line that is identified. And here we have got another function, which is a more complex one. And we have got this kind of typical C shape that we have of the problem. So you can imagine that if I analyze the problem doing what I told, then what happens is that I am learning something about the geometry. And I am intentionally using the word learning because, well, it's not me that I designed the algorithm that is learning, but it's the machine that is learning. So let us move on. What do we do with these points? We consider them as a distribution of points in many variables. So from statistics, when we have a distribution of points in many variables, which means when we have many vectors, what we can do is to calculate a mean vector that is here given by this formula. And then we can calculate this other thing, which is called covariance matrix. A covariance matrix is nothing else but a multivariate version of a standard deviation or variance, and is normally indicated with the letter C. So you can consider that we have got this matrix C, which has got one very interesting feature. It's symmetric. And when I have calculated this matrix C, I can apply one simple algorithm of numerical analysis, a numerical method, which is called the Cholesky factorization, which allows to calculate the eigenvectors of the matrix. So I can then calculate this eigenvector, which are some vectors, and they are the vectors that I'm going to use as the columns of the matrix B, which means the basis matrix along which my algorithm is going to move. So let us at first look at the figure, and then let us comment on it. You can see this is the sphere. We have identified these two directions, the other directions of the eigenvectors. But so here the problem has got the symmetry, so we don't really appreciate that. But in the ellipsoid, we see that these two directions coincide with the axis of the ellipsoid. And here, in the case of the bent-cigar, we identify this two axes, the longitudinal and transversal axis. And here with Rosenbrock, we identify these other ones. So we can immediately see that these eigenvectors have got something to do with the geometry of the problem. And another way of looking into that is that if we are looking at those directions as a new system of coordinates, what we have is that the covariance matrix in this system of coordinates is diagonal. This means that the problem is separable, which means simply that if we move along those directions, or we are moving in a new system of variables, and along these variables, say, the problem is uncorrelated. So these variables are not correlated to each other. So we can move along those, and we are not affecting one variable from another. This might sound slightly confusing, but it will be more clear in a minute. So there is another thing that happens with maximum and minimum derivatives, and I will show that later. So let us now look at this video. So here I am moving a pattern search, just like Fermi and Nick Metropolis say, so horizontally and vertically. And you see that the result is this 976. Here, what I'm doing is to perform the fitness landscape analysis. So you see, I'm sampling it, and I'm transforming my problem of optimization into a problem of data science. And then when I have analyzed the problem, I can identify these two axes. And when I move along this axis, doing exactly the same job as I've done before, so it's the same algorithm, I achieve something in the order of 10 to the power of minus 16. And this is an effect of the fact that the variables are not correlated in that system of reference. And this has to do with linear algebra, with linear mapping, with eigenvector and eigenvalue theory, and essentially how you diagonalize a linear mapping, or equivalently, how you diagonalize a matrix. And this is how this can help in optimization. But this is somewhat a long premise that I'm making today, because I'm going now to criticize myself and this algorithm which was built up a couple of years ago. And what are the limitations? At first, the biggest limitation is that we need some empirical considerations to identify for each problem a specific threshold. If I choose a wrong threshold, then the algorithm doesn't work. Then I have to be very careful, and I need to look at the problem and select something ad hoc before I can actually run it, which of course takes a lot of human time. And that's something that we do not want to have, because we want the algorithm to be automatic. And the second limitation is that this is typically a local search, which means that if the problem is non-convex and has got multiple minima, then what we have is that the algorithm might not work, or probably will not work. So in order to overcome these limitations, I came out with my colleagues with some solutions. I'm going to illustrate the first one. This one is what we call Covariance Pattern Search with Eigenvalue Determined Radii, or for short, Eigen CPS. At first, in order to understand what we are doing, we have to make a consideration. And it is, what's the difference in terms of directional derivatives between the direction of the axis and the direction of the eigenvectors? In dashed lines, we see for a problem, which is the ellipsoid, the directions of the axis. So you can see we have got two certain directional derivatives. But if we choose the directions of the eigenvectors, we find out that along one direction, the landscape is flat, and along the other one is very steep. And that's why it works, because we want to perform steps in this direction, because we know that this allows to improve a lot and quickly. And in this direction, we know that not much is happening. So we still want to move, but take that into consideration. Let us rephrase what I've just said in a slightly more formal way. What we want to do is to perform large steps where the fitness landscape is flat and small steps when the fitness landscape is steep. Because when it is steep, small steps mean that a lot of things are changing. So we want to take small steps, while large steps where it is flat. A bit like if you climb a mountain, or if you're moving. So if you have a piece of land that is flat, you can surely move. But if it is very steep, then you have to be careful, take little steps, and make sure that you don't fall down, or that you are not ending up in an undesired position. So this, what I described, is somewhat the general idea, and at the intuitive level, let us say it more formally. So an efficient pattern search performs large steps along flat directions and small steps along steep directions. And the eigen CPS is divided into local runs. So instead of having a single run, I'm having some restart mechanisms. So which means that I run a CPS for a while, then I perform a short analysis, and then I restart it again. So at each local run, the points are sampled and the covariance matrix is calculated. And the eigenvectors are calculated and used as a basis matrix B. And then something else is performed. The corresponding eigenvalues are also calculated and used to determine the radii along each direction. So that means that now I'm not looking only into the matrix B, but I'm also looking into the step size. So I am connecting the step size to the fitness landscape analysis. And the connection is given by this formula. We'll see what it is, but let's say this is related to step size, is equal to the square root of the eigenvalue lambda. So along the direction identified by the eigenvector pi, I'm going to use a step size which depends on the corresponding eigenvalue. Okay. Here we have, at first, the local run, which means every time starts something, it starts this. And as you can see, we have that this is in yellow, it's the moving equation. You see it's this first part means that it moves alongside the direction of pi, and then this direction is multiplied by this factor, that is the square root of lambda I, and the same happens here. But then here we have, let's say, like a main program that is launching multiple times the local search, and every time is performing the analysis. So here it's happening that we are performing the fitness landscape analysis. So in this 4 cycle, it is happening that we are sampling some points. Then we are putting them into this data structure V, and we are extracting C, or we are calculating C, and then we are extracting the eigen vectors and the eigenvalues. Then we calculate this vector D, and then we pass it down to the local search. But there is something else that is happening. And it is that we are no longer using a threshold which is identified by a user, by a human. But what we are using is a threshold that is identified by what happened in the previous run. So which means that we don't know what the threshold is. We use the best objective function value calculated in the previous local search run. And then you can see that one moves down run after run, and then we don't have to calculate it. And in a way, you may think that the algorithm is progressively analyzing the problem little by little, understanding more and more, or learning more and more from the problem. Now, we have one problem to solve, and or maybe I have a problem to solve, and this to explain you why am I using the square root of lambda I. Now, this can look slightly confusing, but I hope it will be clear. And let us look at the problem in 2 dimensions. So we see that each point in 2 dimensions can be represented as a blue dot on a plane. And this lines here, this dashed black line and this dashed red line are the eigenvectors, or better, the directions of 2 eigenvectors. Now, what is the meaning of the eigenvalue? The eigenvalue is the means, or let's say the meaning is that is this width is the variance somewhat, is the variance of the distribution of points alongside this direction. So here I'm indicating with this arrow. So lambda 2, which is the eigenvalue or related to direction P2, is big, and it means like, yeah, that distribution width. And this lambda 1 means this other distribution. So it means how are distributed according to the other coordinates. So you may see that in this case, we have that along this direction that is long, we get this big eigenvalue. And in this direction, where the distribution is small, we have a small eigenvalue. And in a way, what we want to do is, for what we have said before, is the opposite. We want to take large steps, or we can say, yeah, we can say that we want to take large steps. Actually, we want to do, say, the same, not the opposite. We want to take large steps in the direction of lambda 2 and small steps in the red direction of lambda 1. So what do? We multiply, for that reason, the step size by that square root, by the square root of lambda I. So this somehow explains why it is lambda I, but not completely why the square root. I will use this formula here. So all the mathematical details are actually in this paper, which we published this summer. And what I can tell you is that this here, the fx in the pi, which means the directional derivative along the direction of the eigenvector, is inversely proportionate to the square root of the eigenvalue. So that means that there is an inverse relation between the square root and the derivative. So if I say again, we want, when the derivative is high, take small steps. Essentially, that's what we are looking at, and the other way around. So for this reason, we multiply by lambda I in on the square root. So let us see some results. So here we have a set of functions that we have used. Some of them are actually also multimodal. And we have tested by comparing eigen CPS against CPS, which is what we published. Still, it was published at the beginning of this year. And this other pattern search is actually an implementation from 2008. But the sense is that they are, so this is moving horizontally and vertically, but besides that is the same as CPS, and this eigen CPS is what I've just described. And when we look into the results, we can see that eigen CPS outperforms basically all the, well, these other two variants, clearly outperforms PS, except for the sphere, because in the sphere, moving horizontally and vertically is already the right thing to do. So here we get better results, but in all these other cases is actually performing better. And against the CPS, also it tends to perform better or the same, with only one exception, that is this function F7. And for some reasons, in that case, to apply the classical CPS, or the, well, not classical, I mean, let's say the CPS, the previous version, is paying off, and it seems the best option. But here I show you one result in 50D, and in this case, please appreciate that this is a logarithmic scale. In this case, you see these steps here, these are like the restarts, and you see that for this specific problem, the eigen CPS is performing really well and outperforms the other algorithm. So you can say that this is CPS, and you have that this first half is essentially the fitness landscape analysis. These are located, and then it drops down, and then it keeps slowly going down. PS, conversely, improves at the beginning and then gets stuck. And eigen CPS is, you see here is analyzing, then there is some analysis, and with some improvements and so on, and eventually achieves much better results, at least for this problem. And when we compare eigen CPS against other type of algorithms like BFGS, which is a classical algorithm in numerical optimization, and Rosenbrock method, which is another classical method of the same type, what we obtain is that with respect to Rosenbrock, eigen CPS tends to obtain better results. Rosenbrock, you might track, is an algorithm that also uses something like a change of variables, but it's done in a quite different way. And BFGS is gradient based. It makes an estimation of the gradient, is another classical algorithm that requires to be checked. And you can see it's a very good algorithm, this BFGS. But so on some problems, it outperforms our eigen CPS, and in some others is outperformed by us. So it's possibly competitive depending on the problem that we are looking at. And when we look into this case, so again, we have got the discus, and you see that eigen CPS actually outperforms these other problems. So it identifies the correct rotation and detects better results than the other algorithms. So in conclusions for this part, let's say that fitness landscape analysis is used to determine the direction of the landscape characterized by minimum and maximum derivatives, which is in a way what we wanted to do, and we can estimate in this way the derivatives. We can estimate them through the eigenvalues, which is something that was never done before. And the directions of this special directions are those of the eigenvectors, and that's something that we have found out over the past 2 to 3 years. And so the direction of the eigenvectors of the covariance matrix associated with the sample points, while the derivatives alongside these directions are identified with the corresponding eigenvalues. The proposed logic outperforms CPS, and the proposed Eigen-CPS can be considered as a local search, but with a restart. So in that sense, it can be seen as a memetic approach. If you don't know what memetic approach, it means like a hybrid algorithm that has got some global search and local search. And now I would like to present another study that goes in a different direction from the same premise. And this is what I called adaptive covariance pattern search, and gives the name to this talk. But we may think that Eigen-CPS is also an adaptive covariance pattern search. So that's why I'm using this name somehow as an umbrella name for both these implementations. So let us see at first what is the general idea. ACPS is divided into local runs. In the first local run, ACPS uses B equal to the identity matrix. That is a basis along the directions of the variable. So you have multiple local runs, and in the first one, it uses the same matrix as Fermi and Metropolis. Then, during each local run, ACPS stores the solution that outperformed the current best. So instead of having a separate part where we are performing the fitness landscape analysis, we are collecting the data while we are optimizing. So that's somehow the novelty in this case. And on the basis of this solution, we calculate the covariance matrix as before, and we calculate the eigenvectors. So in this case, we have got only the eigenvectors. We are not looking at the eigenvalues. There is a reason which I will explain in a second. And at each local run, we reinitialize the exploratory radius. So there is some restarting. Let us give one example in order to take the essence of what is happening. So at the beginning, you see that during the first run, you can see that we are moving horizontally and vertically. And then with this data that are collected, it can calculate a covariance matrix. And then it makes an estimation of these two directions. And it moves, but here it doesn't move much because these are not good directions. But we are not wasting computational effort, computational resources. What we are doing is actually learning from the problem. And in fact, then in the following local run, this micro movement allowed to re-estimate a new covariance matrix and a new set of directions, which are these two. And along this set of direction, the problem is it can be solved very efficiently. So you can see that from 399, we move in a few steps to 9 by 10 to the power of minus 13. And at last, there is like so we use these points to another refinement of the covariance matrix. So we are learning the problem more, or the algorithm is learning the problem more, and perform some other micro movements, which allow still some other marginal improvements. This is the adaptive covariance pattern search. So you can see this is a more elegant, this essentially it's my favorite algorithm in this talk, and it's a more elegant and compact. You can see I need only one slide to put everything. And yeah, you can see there is really not much happening, but because I am, let's say, in this case, I'm intelligently using the data in each local run. And so the comments are, we definitely do not need a threshold, because we are simply using as a threshold, as in the case before, the best objective function value of the previous local run. We do not need to do any separate fitness landscape analysis, because we are doing it while we are optimizing. So we are essentially saving, or we are efficiently using the computations that are available. And so we can see that ACPS analyzes the landscape while it searches for the optimum. And the restarting mechanism allows to handle, to some extent, some multimodal problems, because it restarts and then it starts searching somewhere else in a slightly different area. Here, look at this. So you see, first run, it is moving horizontally and vertically, and it's marginally improving. It's not doing much in this case. And but still it's running. Now it has identified new search directions and it's moving them, but now it's identified this other search direction in the 3-1, and you see that now it's much faster, and you see how it is moving in along this direction more and more, and this number is getting lower and lower. We want to get to 0, and then it keeps on moving, and yeah, here it's kind of refining it, and you see 0.6, and that's where it stops. We would have wanted a 0, but this is still a pretty good result. And what is interesting is how the algorithm has learned the problem progressively. Let's see some results. Again, we have got a list of problems, which is not exactly the same as before, but very similar. And we are using, again, the FGS, and we are using, in this case, CMA-ES. The reason why I chose this algorithm is that it also performs something similar. It also has got covariance matrix, but it's not the same covariance matrix. And it also has got some adaptation, and it's probably one of the very best algorithm in for continuous problems. And now it's a 20-year-old algorithm, but still it's very hard to beat, at least for some problems. And you can say that in this case, with respect to BFGS, we get much better results. So this ACPS, which is simpler and more elegant, performs better than the previous algorithm that I explained you, even though does not contain that elegant mathematical proof to connect the directional derivatives to the eigenvalues. But this works better, at least for this implementation. So BFGS is beaten. And the CPS is also beaten, except for this function, which is the same as before, in where CPS is very good. The results with or against CMAS are more mixed, meaning that you can say in some cases this wins, in some cases it loses. So by the way, of course, when you see a plus, it means that ACPS wins. When you see a minus, it means that CMAS wins. And you can say that the results are more mixed, but CMAS is considered to be an extremely good algorithm. So, which means that this ACPS, for being much simpler, so compact, is a good alternative, which can be used in several applications. And on some problems, it is indeed better. Here we have got the results in 50 dimensions. So those before were in 10, these are in 50. And here, the results are slightly different because against the BFGS, you see that there are some points where the search for the gradient is hard to beat, but in some other cases, ACPS actually is better. And so with CPS, there is not much to say. The new version, this adaptive covariance pattern search, is definitely winning. Again, with against the CMAS, we have mixed results where we have sometimes CMAS wins, sometimes ACPS wins. But what is happening is pretty interesting. And it is that when we are in low dimensions, we have the split, and which is confirmed in high dimension. But where, let's say, ACPS wins in 10 dimension, in 50 dimension, it wins by a lot. Where it loses by a lot, which tells us something quite interesting about optimization algorithms, or at least this type, that are indeed specialized for some problems. So you say that, for example, in this F2, F3, and F4, CMAS is excellent, and to scale up the problem does not really present a challenge, while it is a challenge for ACPS, because you see that the performance is deteriorated. So here we had 10 to the power of minus 23, and here we have 10 to the power of 5. While for these other problems, like F5, you see 10 to the power of minus 31, and here we have 10 to the power of 4. So in that case, we have the reverse situation happening. And here we see one example. And in this case, we have, you see, all this kind of staircase trend. It means that we have the restart, and every time it is getting better. So you might think that every time you see this step, it means like that there is a rotation in those axes where the algorithm is moving, while this is the trend of CMAS, which is, well, it goes up and down, or we just got that ripple because it's an algorithm which accepts some marginal worsening sometimes in order to improve better. And it's a very good algorithm. And in this case, we have this pretty interesting result because ACPS is not bad at all, but at last, CMAS adapts better to the problem. So given enough budget, even though here it looks like it is stacking, in reality, at last it rapidly goes down, and eventually it slightly outperforms our ACPS. But when compared to these other two algorithms, we see that these two belong to a certain league and these other two belong to a different one. Comments. So now let's say general comments about the second part and a bit in general. So a relatively low number of points could be enough to estimate the geometry of the problem. So this is something that possibly I have not emphasized enough. And it is that at each restart, it uses those points that were better than the initial one. So those movements that were successful in the search. So what happens is that in ACPS, what we have is a data set which is a way smaller. So we have an algorithm that is lighter. And then we have said a few times that ACPS, unlike CPS, analyzes the landscape while optimizes. And on some problems, it is as good as CMAS. Now, I wanted just to comment about why, in the case of ACPS, we are not using the directional derivatives through the eigenvalues. And the reason is that when we bluntly try to include it, it didn't work. So we do not have let's say, since we have got few points, let's say few points are good enough to determine the directions of the eigenvectors, but are not good enough to estimate the eigenvalues, and therefore the estimation of the gradient is usually wrong. So this is a problem that is open, and I am still looking into it. I don't know yet how to solve it, but what I would like in the future is to combine the features of these two algorithms. So I would like to have something that is elegant and computationally saving, like this ACPS, and also performing like ACPS, but that also includes that nice feature of estimating the directional derivatives of the landscape, so to perform a more complete analysis of the problem, and therefore ideally we have an algorithm that performs well and that is more competitive with against BFGS and CMAS and other complex algorithms that are present in the literature. And this concludes my talk. Thank you very much, and I hope you enjoyed this talk. It has been a pleasure talking to you, and I hope I will talk to you again in the near future. Cheers, bye.